So let's look back at how we can turn a system of equations into matrices. Right? So we did before all the stuff of turning it into an augmented matrix, but there's a couple other things that we pointed out before. So with this system of equations here, what we can do is we can turn this into a matrix equation of this form, right? Where here we think of these are vectors, but we think of vectors think of vectors as sort of m by 1 matrices. Right? So here, instead of thinking of a vector as a row, we think of it as a column here. All right? So this system of equations here, if we write it in this way, we now have a matrix equation. Right? So this is the matrix A. Remember, we called this the coefficient matrix. Here's the matrix X, what we'll call our variable matrix. And over here is a constant vector, or the constant matrix, which represents the constants in the equation. Right? And if you multiply out the left side of this, you can see that we should get, exactly what we expect. 3x1 plus 4x2. In the top row, the second row will be negative x1 plus x2 equals 7 and 0. Right? And if you compare back, well, if these two matrices are equal, then their components have to, or their entries all have to match up. Well, we have 3x1 plus 4x2 equals 7. That's the first equation. And negative x1 plus x2 equals 0, which is the second equation. All right? So, we can turn a system of equations into a matrix equation. So hopefully this gives you an idea of why it's interesting to look at matrix algebra, even from the perspective of solving systems of equations. Because if we can somehow move this a to the other side, that lets us solve for x. So this will be a goal for us in the future. So generally speaking, right, you have here your big matrix, A1n, A21, A22, A2n, and AM1, AM2, AMN. Right, so we can always do this no matter what. x1, 2, dot dot, xn. Oh, sorry, I made a mistake up here. These aren't m by 1 matrices, these are n by 1 matrices. The number of entries in that vector should match the number of columns. Sorry. And this here is B1, B2, Bm. Right, so the size is on this. This is m by n. This is n. I wrote that backwards. N by 1. And this is m by 1. Right, and here this is the coefficient matrix. This is the variable matrix. And this is the constant matrix. Right. And again, normally we're going to write this down as AX equals B. Okay. Now, we're actually at a unique place to be able to prove a very important property about systems of equations. So I'm going to call this a theorem. Right? So for a system of linear equations, right? Precisely. One of the statements below, horrible, statements below are true, right? You can either have the system has exactly one solution, right? You can have that the system has infinitely many solutions, right? Or you could have that the system has no solutions. Or, well, no solution, I guess we don't have that plural. One of these three things has to be true. Okay? So, how do we prove this to be true? Okay. So, let's prove this. This actually isn't that bad of a proof. Okay? So we're going to write the system as ax equals b. Okay? Then, if the system has exactly one solution, or no solution, we're done. Right? So it seems kind of weird to say this here, but we want to show that we have to land in one of these three situations. Okay? So the way we're going to do this is say, well, if there's no solution to that system, then there's nothing left to show. If there's one solution, exactly one solution, then again, there's nothing left to show. So what we're going to do is say, well, what if there's more than one solution? Okay? We need to be able to say that if there's more than one, then there has to be infinitely many. And that'll make sure that, we either know there's none, one, or infinitely many. Okay? Okay. So how do we do this? Okay, so assume x1 and x2 are two distinct solutions. Right, this just means that the two vectors x1 and x2 are different. Okay, that's all that means. All right, so this means ax1 equals b and ax2 equals b. Okay? So, if we're in this situation here, we can sort of subtract these equations from each other. So if we do like ax1 equals b, and then subtract the equation ax2 equals b, then this is telling us that, well, ax1 minus ax2 is 0. Right? Or the 0 vector. Or the 0 matrix, however you want to think about it. Right? Here, I can factor a out to the left, because remember, matrix multiplication is distributive. So this lets me say that x1 minus x2 equals 0. Okay? So, what do we have now? Right? Well, so the vector, which we'll call x sub h, equals x1 minus x2, is a solution of the so-called homogeneous system, which is ax equals 0. Right? A homogeneous system of equations is just a system of equations where all the constant terms are 0. But notice here that 0 is always a solution of that. So there's always at least one. Right? But now we have another one here, the homogeneous solution up here, x sub h. Well, then for any scalar c, we have a times, let's take the vector x1 and then add a constant multiple of this, of the homogeneous solution we made earlier. Okay, well, if we distribute that, that's ax1 plus acxh. Right, and I can factor out that constant. Well, this part right here is just equal to b. Over here we have c axh. Okay, but that's b plus c times axh. Up here, we know that that's got to be 0. So at the end of the day, this is just b. So x1 plus cxh is a solution to ax equals b for any value of c. That means there's infinitely many solutions. Thus, there are infinitely many solutions. All right? So, hopefully that makes sense there. Oh, God. So there's some interesting things we can say about a system of equations when we're allowed to start doing this matrix algebra. We can really nail down sort of this fact that a system should have 0, 1, or infinitely many solutions. Right? Hopefully that made sense, and see you in the next one.